Hi everyone, my name is Tony, and in this video I'll be giving a presentation called Working in Elevators, or how to build an offline-enabled real-time to-do app with LiveView, Svelte, and YJS. Okay, so first off, why am I building an offline-enabled real-time to-do app? And there are two reasons. Reason number one is because I wanted to learn the Phoenix web framework. So Phoenix is a framework that is built on top of the Elixir programming language. And specifically, I wanted to learn two features of Phoenix, LiveView and PubSub. So in order to learn these topics, I decided that I would build a to-do app. That brings me to reason number two, elevators. So for my to-do app, I wanted to make it an app that I would actually use personally. And one of the biggest pain points I've had with to-do apps that I've made in the past is that they didn't work offline. And this is a problem for me because I live in an apartment complex where I have to go up and down this elevator every day in order to get in and out of the building. And whenever I'm in this elevator, I lose internet connection, and therefore my to-do app just wouldn't work. So I wanted to make sure that any to-do app I build must have the ability to work offline. If you're familiar with LiveView at all, you'll probably notice a little predicament here. LiveView is a server-side technology that requires a WebSocket connection in order to work. At a high level, what LiveView does is that it renders HTML on the server, sends it down a WebSocket connection to a client, and then on the client, whenever there are actions that are taken, those actions are sent back up the WebSocket to the LiveView process, and the LiveView process will then render additional HTML and send it back down the WebSocket connection again. And that cycle keeps continuing as the LiveView app runs. So in the case in which there is no internet connection and thus no WebSocket connection, the LiveView app basically wouldn't work. So if I wanted to accomplish my goal of building an app with LiveView, but also make it work offline, how would I do that? After a little research, I was able to come to a solution using Svelte and LiveSvelte. So Svelte is a front-end framework similar to React or Vue.js. And LiveSvelte is an Elixir package that allows you to integrate Svelte with LiveView. And I came to the solution of using Svelte for offline support after I saw a couple inspiring talks. The first one being one by Daniils. In his talk, he created an offline PWA using SvelteKit. And on the back end, he was using Phoenix channels in order to have real-time features. This wasn't quite exactly what I wanted yet though, since I wanted to use LiveView on my back end. However, this talk inspired me to think that as long as I can somehow figure out a way to integrate Svelte with LiveView, I can get offline support working. Which leads me to my next talk by Ryan Cooke, where he did exactly that. He was able to integrate Svelte with LiveView. And following that, I came across a package called LiveSvelte, which was created by Wout. And in this package, Wout basically just implemented Ryan's talk, and he made it into a package in which you can install into any Phoenix application and have support for Svelte with LiveView right out of the box. And with this, I pretty much felt like I had all the missing pieces I needed to create an offline app using Phoenix LiveView with Svelte. Okay, so now I'm going to give a quick demo of my to-do app, and then I'm going to round back and explain everything in more detail. All right, so on my screen right here, you should see two browsers. On the left side, we have the to-do app running in Chrome. And on the right side, we have the same app, except running in Safari. And what this app does is it's pretty simple. We can add in some new lists. I guess this one should be called new list without an S, so we can edit that. And I'm going to add another to-do list called to-dos. And as you can see, as I'm adding these lists over here in Chrome, all the changes are being broadcast over to Safari. And if I were to add some items to my to-dos list, all the changes again are being broadcast back to Chrome. And all these changes, they are being broadcast via Phoenix PubSub. Okay, so now that we have a basic idea of how the app works, I'm going to turn off my server to simulate being offline. So as we can see in the console down here, there's an error message which shows that our WebSocket connection has disconnected and we're trying to reconnect. However, if we were to add in another new list right now, everything still works. I can still go into the list and also add in some to-do items, and that still works. And I can even refresh the page, and the app will still work as expected. However, if you notice up here, it's showing not synced because we're not connected to the server. Additionally, because we're offline, all the changes are not being broadcast over to Safari from Chrome, and that's to be expected because we're offline. However, we now have another problem, which is we have different states on different clients. So, for example, let me add in another new list here, and let's call it new list from Safari. And then I'm going to add in another new list here called new list from Chrome. So now we have two clients that are both offline, and they both made changes, so the state is different on these various clients. So ideally, what we want to happen is when we go back online, for all these changes to be broadcast to each other and all the states to merge and converge to the same state everywhere. So let's see if that happens. Going to now turn on my server again. Okay, so it looks like we are now back online. Both clients have now been synced, and as we can see, all the changes from one client has been broadcasted over to the other client. So here we have our new list from Chrome over in Safari, and we have our new list from Safari over in our Chrome client. And that's pretty much it. So what we saw was our app can work offline. It can sync real time, and it can also have the ability to merge conflicting states when it comes back online. Okay, so how does all this work? To answer that, I'm going to first show how a basic LiveView application works, and then I'll build off of this example to show how to add in offline support. In this slide right here, we have our server on the right-hand side, and on our server, we have our LiveView process running. And then on the left, we have our client, and in the client, we have our DOM, our HTML, and then everything is being controlled by our app.js. In a typical LiveView application, a WebSocket connection is established between our client and server. And then the LiveView process will send HTML down through this WebSocket to our client. And then whenever there are any client-side interactions, events are fired up through the WebSocket back to the LiveView process. The LiveView process will process these events, and then if there are any UI changes, then it will send HTML down through the WebSocket to update the client. And then this cycle pretty much just keeps continuing as the LiveView app runs. However, if we were to lose internet connection and therefore no longer have a server or WebSocket connection, then our app no longer works. Okay, so the first step to adding in offline support to our LiveView application is adding in the LiveSvelte package. And as I mentioned earlier, LiveSvelte is a package that allows you to integrate Svelte with LiveView. And what that means is, in addition to sending down just HTML from our LiveView process, our LiveView process also has now the ability to render Svelte components. And in addition to that, we can also update these Svelte components from the server by setting down Svelte props. This is also sent down as HTML over the WebSocket. Okay, so let's take a look at what this looks like in code. On the top right here, we have a LiveView module. And in the LiveView module, we have a mount function where I'm assigning a variable named count with a value of 0 to our socket. And then down here in our render function, instead of rendering a Phoenix function component, I'm instead rendering a Svelte component. And this Svelte component is taking a prop named count, where I'm assigning the count that we previously had set in our socket up here. And then down here, we have a handle event callback, listening for an increment event. And then every single time that increment event is received, we're just incrementing the count by 1, reassigning it to the socket, which then triggers a re-render of the Svelte component. If you're familiar with LiveView, then this should look super familiar. In fact, the only difference between this LiveView module and a typical LiveView module is the fact that we're not rendering a Phoenix function component, but instead we're rendering a Svelte component. So let's take a look at what that Svelte component looks like. So down here, we have our Svelte component, and at the top of the file, we have a script tag and export let count. Export let is Svelte syntax for accepting props. And right here, we are accepting a prop name count that we assigned up here. And then we also have a button where we're displaying the count. And then we have a Phoenix click attribute that will send an increment event up to our LiveView each time the button is clicked. Okay, so now let's take a look at what this looks like in the browser. On the window right here, we can see that we have our button rendered. And whenever I click this button, what's happening is that we're sending the increment event back up to our LiveView, which then increments count by 1, and that triggers the re-rendering of our Svelte component. Now, where this gets interesting is currently the state of the count is only stored in the socket. But what Svelte will allow us to do is also keep some client-side state. So for example, I can define a variable called client-only-count, and I'm going to initialize it with the same count that we got from the socket. And then I'm going to add on another button here. And what this button does is it will display our client-only count, and then on click, we will increment that client-only count. So now in our UI, we have two buttons. This top one is the one that is displaying the count from the LiveView socket. And down here, we have a button with our client-only count, which has state on the client side. And why this is important is because now we have the ability to keep state if we're offline. So I'm going to now turn off my server. Okay, so now we are disconnected from the server. And if I try clicking on this top button, the button no longer works. However, if I were to click this bottom button where the state is being managed by Svelte, the button will still work. So this will give a pathway for us to start building our offline app. So our app works offline now, right? Kind of. There are definitely a few things we still need to consider, such as how do we persist data when we're offline? How do we handle page reloads? And what about conflicting client and server states? We're going to tackle each one of these issues one at a time. The first issue we have is data persistence. When we are connected to our server, we have access to a server-side database, and we can persist all of our user data here. However, when we are disconnected, even though Svelte can keep track of client-side state, all of that data is in memory, which means if the user were to navigate away and then back again, all of that data will be lost. So we need a way to persist this data when we are offline on the client side. The answer to this problem is actually pretty simple. All we have to do is add in a client-side database. And we have some good options for that. For example, we can use IndexedDB or local storage. The next issue we have is handling page reloads. As our app currently is, let's say it was already loaded when we have internet connection, and then we get disconnected. And in that case, the app will still work because we have our client-side JavaScript and Svelte running the app, and then we can also still persist the data. But if we were to do a page reload, this means we will be sending a new request to the server, which is disconnected, and therefore we will get back an error response. And this will mean we won't get the HTML response expected in order to reload the app. So to solve this issue, we're going to have to add in a service worker. A service worker is a browser feature that allows you to register a JavaScript process that runs in the background separate from the main thread. And this background process has two features in particular that will help solve our problem. Number one, it has the ability to intercept fetch requests. And number two, it also has the ability to cache responses that it gets from the server. Let's see how this works. So let's say we have a request that's being made from our main app. The service worker is able to intercept this request, and then it can forward it on to our server. And then when we get a response back from the server, the service worker has the ability to cache this response. So for example, we can cache the HTML, CSS, JavaScript, or whatever other response we get back from the server. And then from there, we can just forward that response back down to our main app. So now let's say our server is offline, and we make another request from our main app. The service worker will intercept this request, and inside our service worker, we can have logic to check whether or not the server is connected or not. If not, we can just go ahead and return a response from our cache. And this solves our problem of handling page reloads. In addition, this means that our app now fully works offline. Our app still runs because we're using Svelte. We're able to persist data with a client-side database, and we can handle page reloads. Okay, so we're almost there. We now have an app that works offline, but we still need a way to figure out how to sync real-time across multiple clients without any conflicting state. To figure out this next part, I'm going to first show an example of how a typical LiveView application works with Phoenix PubSub and a single database where we have our app state. Then I'm going to build off of this example to show how we can manage distributed app states. In this diagram right here, we have multiple clients, each connected to a single LiveView process, and each LiveView is connected to a single database, which is holding our app state. Additionally, each LiveView is also connected to our PubSub system. In this setup, whenever a change is made on a client, that change is sent up to our LiveView and saved to the database. So let's just say that now the state is equal to A. And then this new state is then published to our pub subsystem, and then the pub subsystem will broadcast out this new state to every single LiveView. And then each LiveView will then broadcast the state down to each client, and then the UI will be updated accordingly with the new state. This works great when we have a single database and everything is connected via WebSockets. However, in our offline app, we have multiple databases, and each database potentially can have a different state. So, how do we manage this problem where we have distributed app states without running into conflicting states? After doing some research and asking a couple friends, I found a solution, and that solution is CRDTs. CRDTs stand for Conflict-Free Replicated Data Type. And honestly, it sounds a little scary, but I promise it's not that bad once you get the basics. So what exactly are CRDTs and how do they work? A CRDT is a data structure used to store state locally on different peers. The state can be updated locally and instantly by each peer without having to check with other peers first. In order for these states to eventually converge to the same state, the peers will send updates to each other. And the important part is that these updates can be applied in any order and even multiple times, and the resulting state will always be the same. Let's look at a super basic CRDT example. In this slide here, we have state 1 with a unique ID of 1, a timestamp of 1, and a value of A. And then we have our state 2 with the same data structure, unique ID 2, timestamp 2, and a value of B. So what we want to do here is we want to merge these two states together. And what we are implementing here is a last write wins CRDT algorithm, which means we want the state with the higher timestamp to be the resulting state. So below we have our two merge functions, and in the first clause, we are checking to see whether or not the timestamps are equal, because if they are, then we have a tie. And in order to break the tie, we would compare the unique ID of the two states. So in this case, if we had a tie, the state 2 would win because it has the higher ID. But in our case, the timestamps are not the same, so we can go to our second function clause down here. And in this merge function, we are simply just comparing the timestamps and returning the state with the higher timestamp. In our example, this means state 2 will win because it has a timestamp of 2, whereas state 1 has a timestamp of 1. One other thing to note is that, as I mentioned on my previous slide, we can merge state 1 and state 2 multiple times and in any order we want, and we're always going to get the same resulting state. In this case, state 2 is always going to win because it has the higher timestamp. Okay, so we now know how a basic CRDT works. However, as the title of my slide implies, this is just a super basic CRDT example. In practice, implementing CRDTs can be a lot more complex. Therefore, for my project, I decided to use a library. And the library I decided to use was YJS. YJS is a CRDT library implemented in JavaScript. And the reason why I decided to go with this library is two reasons. The first reason is because YJS is one of the most used CRDT libraries in JavaScript. And the second reason is because you can run YJS on both the client side and server side. Okay, so let's take a look at what our app looks like now with CRDTs. We have our servers with our LiveViews connected to a single database, and each LiveView is also connected to a client. And each client also has its own database. To make things simple, every single database is going to start off with the same state of A. So now let's say that we have a change on our top client and the state changes to B. The nice thing about CRDTs is that we can instantly update our UI without having to make a trip to the server. After updating the UI, we can go ahead and send a request to merge our state to the server database. And thanks to CRDTs, the state will merge without any conflicts. Then we're going to push our new state to our pub subsystem, which will then broadcast it out to the two live views, and then the live views will broadcast it down to the client. On our top client, nothing's going to change because we already are at the right state. However, on the bottom client, we will merge our state again to state B, and then we will update our UI accordingly. And there you have it. We now have a to-do app that can work offline, can sync real-time without any conflicting state, and it's all built with Phoenix LiveView, Svelte, and YJS. Some closing thoughts. So first off, I'm still not sure whether using Phoenix LiveView for building an offline app was the best choice, but I'm not complaining because the app is working really well. Secondly, I think I was able to meet all of my goals, so I'm pretty happy. I was able to meet my goal of learning Phoenix, particularly LiveView and PubSub. And secondly, I now have an app that works in elevators. I know I went through some of the topics pretty quickly, so if you would like to see more detail on anything, please feel free to check out the source code. It's available on GitHub. And if you would like to see a live demo of the app is live on fly.io. And lastly, if you have any questions for me, please feel free to contact me. Links to my social and email can be found on my blog at tonydang.blog. Thanks for watching.